Hey everyone! Welcome back to my channel. Today, we're diving into something super exciting. We're going to build our very own face recognition attendance system using FAISS. And the best part? We'll be using 100% local open source technologies. Let's get started. This AI app can search through about 10,000 images with a response time of 7 to 10 seconds on a CPU, and it performs even better on a GPU. First, let's talk about FAISS. What is FAISS anyway? FAISS stands for Facebook AI Similarity Search. It's an open-source library developed by Facebook, designed for efficient similarity search and clustering of dense vectors. It's widely used for tasks involving nearest neighbor search in high-dimensional vector spaces. FAISS is optimized for both speed and memory efficiency, and it supports both CPU and GPU acceleration. In this series, we'll build our own face recognition attendance system with FAISS using 100% local open-source technologies. Now that I've got your attention, let's build this application step by step. Let's see our face recognition app in action. We are going to build an app with a chatbot interface. Users can type their questions into a prompt window. The app will capture these questions and process them using a local face vector database. We'll dive into the details of building this code later. For now, let's focus on how our app functions and the results it produces. Here is the process is going to look like. Step 1. The user uploads an image. This is where you provide the image you want to search for. Step 2. We convert the image to a vector. The app transforms your image into a vector, which is a format that FAISS can work with. Step 3. The app searches the FAISS database. Using the vector, the app searches through the FAISS database to find similar images. Step 4. We display the closest matching image. The app then shows you the image from the database which is closest matched to your uploaded image. Finally, results will be displayed to the user closest matching image from the database alongside the original uploaded image. Now, since we got an idea what app is going to look like, let's start building it. Let's first install FAISS on local machine. Please open a web browser and visit https://ai.meta.com/tools/FAISS. Here you will find FAISS installation instructions. Please keep in mind that FAISS is still new and rapidly evolving. Always refer to the latest updates on the official GitHub repository documentation, as instructions might have changed by the time you are watching this. Currently, the supported way to install FAISS is through Conda, but we will install it through pip. Just open a command prompt window, and for CPU installation, type pip install FAISS CPU. And for GPU installation, type pip install FAISS GPU. Now, since we got FAISS installed, let's understand basics of FAISS. Let's dive into the fundamentals of similarity search. This concept is crucial for understanding how we can efficiently find and compare similar items within large datasets. Let's see how FAISS similarity search works. First, it looks into a set of vectors. Vectors are essentially lists of numbers that represent data points in a multidimensional space. It creates a data structure, called an index, in RAM. This index helps organize the vectors in a way that makes searching through them much faster. Once the index is built, it efficiently performs search operations. This means it can quickly look through the indexed vectors to find the ones that are most similar to a given query vector. Finally, it finds the vector with the smallest Euclidean distance, argmin, to the given query vector. The Euclidean distance is a measure of how far apart two vectors are in the multidimensional space, so the vector with the smallest distance is the most similar to the query vector. In summary, FAISS helps you quickly find similar data points by organizing and searching through vectors efficiently. Let's take another look at FAISS internal processing. The index has an add method to store vectors. Vectors are lists of numbers that represent data points in a multidimensional space. When you use the add method, you're essentially telling FAISS to remember these vectors for future searches. It assumes the stored vectors remain fixed. This means that once you've added vectors to the index, FAISS expects them to stay the same and not change over time. This assumption helps FAISS optimize its search operations. It efficiently performs add and search operations. FAISS is designed to quickly add new vectors to the index and search through the existing vectors to find the ones that are most similar to a given query vector. In simple terms, FAISS is all about building this index and using it for fast vector searches. By organizing the vectors in a smart way, FAISS can quickly find the most similar vectors to any query you provide. Now, since we got basics of FAISS, now is the time to learn about Euclidean distance. Let's try to understand fundamentals of Euclidean distance. In this section, we will see how to calculate Euclidean distance, which is used a lot in FAISS. Euclidean distance is the straight line distance between 2 points in a Cartesian plane or space. It is calculated using the formula. This formula works by finding the differences between the coordinates of the 2 points, squaring them, summing the squares, and then taking the square root. As you can see in this diagram, Euclidean distance is the straight line distance between 2 points in a Cartesian plane or space. Now, since we understand how to calculate Euclidean distance, let's work on a sample image. Let's start by understanding the basics of working with images. First, we'll look at a simple example of a tiny image. This is an example of a 2 by 2 pixel image. In reality, this image looks like this. Each pixel is a different color: red, green, blue, and yellow. This pixel image is stored as a NumPy array. When you print it, it looks like this. The shape of this array is 2 rows by 2 columns with 3 channels. When you flatten this array using the reshape method, it looks like a long vector in memory. Let's call the number of elements in this flattened array dimensions. In this case, we have 12 dimensions representing one image. Now, let's take another example. This time, let's create 3 image arrays, each 2 by 2 pixels. Let's write the code to create image A, image B, and image C. In reality, these images look like this. As you can see, each of these images has exactly 4 pixels, arranged in 2 rows and 2 columns, and they are colored red, green, and blue. These pixel images are stored as NumPy arrays. When you flatten the red image vector using the reshape method and print it, it looks like this. This is the flattened version of one image. So now, if we write another code to vertically stack all of these 3 images and put them in different rows, we get a new array. Now, let's flatten each image and stack them together using the stack method. Let's store this in a DB vector. Our DB vector is a tiny database of 3 images of flattened vectors. Each row represents a red, green, and blue image. As you can see, there are 3 rows, one for each image. Let's calculate the number of elements per image in this flattened array as 2 by 2 by 3. So, in this case, we still have 12 dimensions in this index to deal with. Now that we understand how images are stored as vectors in memory, let's write the code together. First, we'll flatten and stack the red, green, and blue channels of an image into a single array called vec_base. This array will serve as a compact representation of our image data. Next, we'll flatten the blue channel of a query image into a separate array called vec_qry. Think of the vec_base array as a tiny FAISS database containing vectors of all 3 images. The vec_qry vector represents the image you want to search for within these 3 images. Our objective in this exercise is to find the closest match of the query vector, vec_qry, within the given 3 base image vectors, vec_base. This process involves comparing the query vector to each vector in the database to determine the best match. By the end of this exercise, you'll have a clear understanding of how to manipulate image data using NumPy arrays and how to perform basic image search operations. Let's get started with the code. In other words, vec_base looks like this and vec_query look like this. First, we will need to import the FAISS library, which is a library for efficient similarity search and clustering of dense vectors. It's particularly useful for handling large datasets. Here, we define two variables. D represents the number of dimensions of the vectors we are working with. In this case, each vector has 12 dimensions. K represents the number of nearest neighbors we want to find. Here, we are looking for the single nearest neighbor. This line creates an index for our vectors using the index_L2 method from FAISS. The L2 stands for L2 norm, Euclidean distance, which is the distance metric used to compare vectors. The index is built to handle vectors with d dimensions. Then, next line adds the vectors stored in vec_base to the index. Vec_base is assumed to be a NumPy array containing the vectors we want to index. This line performs the search operation. It searches for the k nearest neighbors of the vectors in vec_qry within the indexed vectors. The results are stored in two arrays. D contains the distances of the nearest neighbors. I contains the indices of the nearest neighbors. And finally, these lines print the indices and distances of the nearest neighbors found. Indicates that the nearest neighbor to the query vector is the first vector in the index, index 0, and the distance between them is 0. This suggests that the query vector is identical to the first vector in the index. Now we understand how to create FAISS index on a sample image. Let's move to next section. In this section, we will work with real images. Let's load real images which we want to use in your app. In this example, first import necessary libraries such as NumPy for numerical operations, PIL for image handling, matplotlib for plotting, and FAISS for similarity search. Then load and display an image from the specified path, and displays it without axes using matplotlib. When you display the image, it will show your employee images. In this example, I used images of cats and dogs. Note that I combined 6 animal images into one just to show them all together, but you will have 6 images. Ensure all images are the same size, crop them if necessary. Now, let's load these images into NumPy arrays. As you can see in this code, there are 6 different images loaded into 6 NumPy arrays. Now, flatten these images into flattened array and stack them together so that we can load these into indexes. Let's define dimensions equals 392832, which is calculated as the image width times height times 3 for the 3 color channels, red, green, and blue. This value represents the total number of values in a vector array for an image. Next, we set k equals 1. Here, k represents the number of nearest neighbors we want to find in our similarity search. Setting k equals 1 means that the search will return only the closest matching result. Now, write index equals face.indexFlatL2d, which creates an index using the L2 Euclidean distance metric for vectors with d dimensions. And index.add employee_db adds the vectors from employee_db to this index for similarity search. When you run the search, it will return the index of the closest matching image from the database. For example, if you are searching for an image of an employee, it will return the index of the image in the database that is most similar to the query image. In next section, let's add some more random NumPy arrays to test system performance. Now, since we have got some images working, let's experiment with 10,000 images. In this section, we will load 10,000 NumPy arrays to test index performance. Since we don't have 10,000 images currently available, I am going to generate random set of image arrays using NumPy. This code generate 10,000 such arrays. If you recall from previous section, these are the 6 images we already had in image arrays. Just like we mentioned in last step, we will flatten these images and stack these together. However, this time, we will add flattened version of the new additional rows we created, so after you execute this step you will have 10,000 plus 6 images in image vector array. Let's define dimensions equals 392832 and k equals 1. Dimensions d is derived from image width times height times 3, where 3 represent RGB color channels for each pixel. Dimensions is the number of values in a vector array and k is nearest neighbor similarity search. When k equals 1 means it will return only first closest matching results. Index equals face.indexFlat L2 d creates an index using the L2 Euclidean distance metric for vectors with d dimensions. Index.add employee_db adds the vectors from employee_db to this index, enabling efficient similarity searches. This code searches for the nearest neighbor of the query vector vec_qry in the index and returns the indices I and distances d of the closest matches. The output 0, 0 indicates that the closest match is the first vector in the index with a distance of 0, meaning they are identical. Eventually, this closest matching image index is the index of your employee image you are searching into database. Now this was very simplified version of storing and querying real-life images. You will notice that depending on your machine, response time may vary, but still on a good moderate PC, for 10,000 images I was able to get 7 to 10 seconds response time. And with GPU, obviously performance will only get better. In next section, we will build an app to create this functionality. In this section, we will build a Python app to serve image processing functionality. Face recognition application. We will use an open source library called Tapy to build this application. So browse to tip.com, look for their documentation section. There is section for gallery where you can download their pre-built source code. Click on LLM Chatbot. We will use this code as is to build a LLM chatbot at first. Now click on their GitHub link. This will take you to their GitHub repository, and please download entire source code from this folder. Please see that I will not cover all the details in this section. I have published a separate video about this where I discussed all the details. If you browse to my X account, which goes by handle ashucklax, under Highlights sections, you will find this video which you can use to learn more about it. Also, if you browse to my YouTube account, which goes by handle amit.shukla, under videos or playlist sections, you will find this video which you can use to learn more about it. Now when you go to these links, please consider following my X handle ashucklax and subscribing to my YouTube channel amit.shukla. I assume at this point you have copied over all GitHub code locally. Open a terminal window and type this command pip install and then run python serve main.py. Now, if everything is installed correctly, you will see an application running on your local host like this. Again, if you have any trouble following these instructions, please consider watching those video links I shared earlier. Also, if you still see issues, please open an issue log at my GitHub repository. Links are included in description below. Now let's include FAISS functionality to this app. In this section, we will customize Python app to serve image processing. Customizing face recognition application. I assume you have already downloaded Tapy sample code from their GitHub repository. Once you download, open main.py file in your code editor. As you can see, it will look like this. Let's first take a minute to review this file, and then we will jump on to code. There are 2 sections we will need to update and add 2 more sections to make it work and customize it. First, we will fix the import statement. Second, we will update sendMessage method, which actually calls a GPT, so in our case, we will simply update this to query FAISS instead. Next, we will need to add code to create /build FAISS indexes. We will also need to update the UI to add a file upload button. Then simply we will add a function to call and handle this image upload. If you find this too tedious, please visit the link to my GitHub repository included in video description below, which you can download and see it for yourself. Let's first get rid of all the imports we had and replace it by this code. As you can see, I simply remove all LangChain and other packages which are not going to use and instead added those packages like FAISS which we need. Next step is to add section which let us do the file upload. Now, let's add our file upload element. This will allow users to upload images that we can process and search within our database. First, create a function that handles this file upload. This function will be responsible for receiving the uploaded file, reading its contents, and converting it into a format that we can work with, such as a NumPy array. Next, let's update the query LLM, large language model, function to take this file input. This function will process the uploaded image, create a flattened array from it, and then query the FAISS index to find the closest matching image. This involves reshaping the image data into a vector that matches the dimensions of our indexed vectors. Finally, display the output of the closest matching result. This step will involve taking the result from the FAISS search and showing the user which image in the database is the closest match to the uploaded image. You can present this information in a user-friendly format, such as displaying the matched image or providing relevant details about it. That's all I wanted to cover in this video today. Please note that this is a very basic version and is not intended for production deployment. However, I can't wait to see how you customize this app and make it production ready. Thanks for watching.